All right, we're back. We are on notes 23. We're going to be on page 5. And we are just talking about slope fields and how we can identify them, what kind of properties we can see from them, all kinds of things like that. So let's take a look at these problems. So what's really nice is that more often than not, you're given a slope field and asked questions about it. It's not really, like if you remember the first page of the notes where we made the horrifying slope field with like 81 points on it, that was a nightmare. Even on the next page, we had tables and we were able to like, in an organized fashion, come up with a way of generating the little line segments and then putting them in. Still pretty bad. On the AP exam, you pretty much never do more than like 9 of them. And when they're checking them over, they are mostly looking for if a slope should be 0, is it 0? If a slope should be positive, is it positive? Because, you know, you have like 300,000 of these. You got to grade 9 points, 9 little tangent segments for each. And then additionally, it's like the whole problem is probably worth 1 or 2 points. So like, what do you do if somebody messes up 1 or 2 of those? I don't know. So get your 0 slopes right, get your positive slopes right, your negative slopes right for sure. Try to get them slanted the right way. Do the best you can. We're lucky though, because most of the time we're given the slope field. And then it's just a question of like, do you know how slope fields work? And so let's take a look at these and see if we understand kind of the subtleties between these two slope fields, right? So dy dx is x and dy dx is x over 2. So very similar. You can look at it. You probably initially immediately have a feeling about this, but I want to answer the question first. What do they have in common, right? So look at the two slope fields. I'm going to say solutions decrease until x equals 0, increase after x equals 0. They all have relative min at x equals 0. So I'm just picturing solution curves. And like, you don't really need to picture them. You could draw them if you wanted to. You know, here, and then maybe like here. So one of the reasons you look for 0 slopes is like they're super good places to like start your solution curves if you get to choose. But what else do they have in common? All of the solution curves are concave up. And I mean, they probably have a million other things in common. I don't know. They're quadratic, right? All the solution curves look quadratic. Now the question is, how can I tell the difference between the two curves? So like, which is which? One option is to actually just pick a point, right? So if I select the point 2, 2 for both of these, so 2, 2, I think is going to be about here. And then 2, 2 over on this curve, I think is going to be about here. Okay, so now the problem is because I put a point there, you can't really see the little segment anymore. But if x is equal to 2, then dy dx, so I'm sorry, where am I even doing this? Okay, so there's a difference, right? If x is equal to 2, then for this, so if x equals 2, dy dx will just be 2. So it's steep-ish. Here, if x equals 2, then dy dx will equal 1. It's less steep. So which of these is less steep at the point 2, 2? This must be x over 2. This must be x. So finding where the slope is 0 doesn't actually help in this case. Picking a point and checking it will work. And it tends to be the more extreme, the better. So like maybe I should have looked at like 4, 0. That's kind of helpful. Or like at 1, or x equals 1/2, let's say. At x equals 1/2, I think that this slope field on the right, so I think this is probably 1/2. I feel like that slope field is way less steep than this, where way less steep is like, I don't know. Also, if you don't have the same scale on your slope fields, it's like, forget it. You're not going to be able to do it. But you're not going to be put in that position, so you don't really actually need to worry about that. But if you cannot tell which is which, pick a point. So plug in a point to both of them, And it should clear it up. If it doesn't, pick another point. If that doesn't, pick another point. Keep picking points because these are very similar. Like sometimes you can look and be like, oh, a point in the second quadrant on one of them gives you negative slopes. A point in the second quadrant on the other one gives you positive slopes. Then it's very clear which is which. Not the case here, which I deliberately picked these. Oh, another thing I would add about what the slope fields have in common is that the slopes along vertical lines are constant. So slopes along vertical lines are constant, which means there's no y in the differential equation. We knew that going in because we were actually given the differential equations, but if we didn't know that going in, that would be incredibly useful information. So let's take a look at these. We need to decide which is which, and we need to say how we know. Well, okay, so what I look for always is zero slopes because that's the most useful, it's kind of the fastest way, right? So here I see a lot of zero slopes, and then on this one, I see zero slopes over here. Otherwise, these are very similar, right? Along vertical line segments, the slopes are always the same. On vertical lines, I should say, the slopes are always the same. So there's no y in your differential equation. Both of them change from decreasing to increasing at some point. All the solution curves have relative minimums. There's, the only thing really distinguishing them. Well, now, I mean, I shouldn't say the only thing. So for example, on this one, if you didn't know which was which, so at this point, I know that because the slopes are 0 when x equals -2, so I know that dy dx has to equal 0 when x equals -2. So then that means that dy dx must be x plus 2 in this case. And then the same exact argument could be made here. This is x equals +2. I know dy dx will be 0. And if that's the case, then I know that dy dx must be x minus 2. So I've definitely been able to choose between them. The way I knew was the location of the zero slopes. So location where dy dx equals 0, which is almost always enough, right? What if that wasn't working for you or whatever, you just don't know, right? I'm gonna choose to look at the point, in this case, I'll switch colors. I'm gonna look at the point 0, 2. I don't know why I don't look at 0, 0, but I don't. So at 0, 2, for this curve, at 0, 2, dy dx is greater than 0. Whereas on this curve, at 0, 2, dy dx is less than 0. And then if you go up to your two differential equations and plug in x equals 0, so for dy dx equals x plus 2, when x is 0, you get +2. For dy dx equals x minus 2, you get -2. At that point, you know how to choose between them. So that's another way that we can choose between them. And for a second there, I thought I actually got these wrong, but I did not. I just, like, my brain wasn't working, which, it happens. All right, so picking a point, very effective. Looking for zero slopes, very effective. Show that all solution curves to both differential equations are concave up. Okay, so I'm going to actually solve an even more general problem. So dy dx equals x plus 2, dy dx equals x minus 2. I need to show that those are concave up. I'm going to show that if dy dx equals x plus c, so if dy dx equals x plus c, which both of these differential equations are of that form. So if I can show that this always has solutions that are concave up, I will have done it when c equals 2 and c equals -2, and we're good. So I'm going to find the second derivative. That's a weird d there. I don't like that. Get out of there. Okay. There is actually just 1, which is greater than 0 for all x. Therefore, solutions are concave up. Okay, and both of our differential equations are of this form, so we answered that question. And that was like pretty simple because it didn't, usually you have to use, I don't know what this thing is doing. It's just like zooming in and out on its own. Usually you have to use implicit differentiation on problems like that, but in this case we didn't, and that was good. So that'll make it a little quicker for us. So always concave up. Anything else that we know about this? I don't know. We could so then you could prove that for like the left hand thing here for this one, we could prove that you always have a relative minimum when x is -2, right? Because dy dx equals 0. The second derivative is positive, so by the second derivative test, you definitely have a minimum. Same thing on the right-hand one. You could prove that there's always a minimum when x equals 2. Things like that. Those are things to think about. Second derivative test, you're going to use a ton. So this page is in the books, so I'm going to stop here, come back in the next video, and do just more stuff. So I will see you there. And I'm trying to find the stop button. So I got it. See you there.